All right, everybody, we're going to go ahead and get started. We might have some more people trickle in. So if I repeat myself, just want to reiterate to anybody hopping in. My name is Troy Daniels. I'm trainer here at SimpliPhi Power. Today, we're going to be talking about AC and DC coupling, PV systems, and how that, in respect to SimpliPhi products, batteries, but also in general terms as well. Just a little bit of housekeeping. If you have any questions, Q&A, go to that black control bar and you can go ahead and type any questions in there. At the end, we will go through all the questions and try to answer as many as possible. A few other items, if you need NABCEP credits, so this is CEU approved. If you're looking for those continuing credits, there'll be an email at the very end. I would just ask that you email me at that email and just ask for credit with your full name. All right, let's hop right in. Okay. So just a little bit about SimpliPhi as a company. I won't spend too much time on these kind of opening slides. Really, just as an FYI, if you are new to SimpliPhi products, this is really more of an advanced webinar related specifically to this topic. We're not going to talk too much in general terms and really kind of talk, about SimpliPhi as a company and our kind of standard products and things like that. We're going to really dive into this specific topic about AC and DC coupling. However, I do have a few slides to kind of tie everything together and bring us in. So about SimpliPhi Power, we were actually founded as OES Energy in 2010. We really kind of looked at as what we saw as a problem, and that was, lead acid batteries and lithium batteries, while new at the time, still being used, but the chemistry at the time that was mostly used was not safe and tended to have a short lifespan. So we really wanted to look at how can we find a lithium chemistry that is both able to be affordable, strong, long lasting, cleaner, as well as safe, which was the biggest aspect. So in 2011, 2012, we actually had the opportunity to work with the Department of Defense and kind of prove that our batteries using lithium iron phosphate were safe, reliable, and could last for what they needed it for. At the time, the military was actually saying no lithium batteries at all due to some thermal runaway events with other batteries and other chemistries. And we were able to put our lithium iron phosphate batteries to the test. No failures, no issues, and really actually got to prove out that this battery was what we said it was. From there, we continued to expand our product lines and actually even relaunch the SimpliPhi Power. We've been ramping up manufacturing ever since, trying to make sure that we keep costs down, as well as conscious about our manufacturing line. So again, we use lithium iron phosphate is the chemistry that we use in our batteries with this cylindrical form factor. If you want to kind of get granular on what's actually in the SimpliPhi battery. A little bit about kind of what we see as the big picture here, kind of some of the reasons why people are going with energy storage, escalating energy costs. We can look at the current figures of, 15% in the last 10 years. This is going to keep going up. Realistically, it's pretty hard to imagine that this number will go down. It might plateau, but most of the time, if you look at trends, energy cost continues to go up when you're looking at grid cost. Failing infrastructure, we're seeing this more and more. Texas being a huge example right now, during the ice storm and now the heat, and, planned power shutoffs here in California, you're probably used to that as well. So we definitely see that as one of the biggest reasons that people are moving towards, distributed assets and looking at how to build resiliency on their own homes. Decarbonization will always be play a role in what we do, and I think why people go with batteries, not necessarily the biggest factor, but it does have a lot to tie into our economic growth and rising population costs, things like that. So These actually are going to be important. I think these are good to look at. So I think a lot of what people do with AC and DC coupling, especially when we're looking at grid tied systems, has to do with using the battery and the solar in a manner that benefits the customer. So some of the big ones that I always look at: peak shaving and time of use. Peak shaving being, if your demand goes above a certain amount of power, you get charged for everything over that at a certain rate. Batteries help mitigate that. So I don't see this as much on a residential scale, but I do see a lot of commercial stuff where this is a big factor. Time of use, I would say, is one of the biggest, and we'll get into this later, but it's definitely the biggest thing when we look at, added benefit of a battery solar system, and really adding, even, if we're looking at AC coupling and adding on, there's a few options there. DC coupled, tons of options there to be able to mitigate these time of use charges that customers are seeing. So really integrated solar plus storage, distributed assets, driving this industry. So that's kind of my fluff, a little bit, you could call it, of kind of the overview, just to kind of slide into the presentation. We're going to kind of go through this through AC, through DC coupling. I'll start with some kind of basic definitions. And, I apologize if you're like, this is kind of review. We can start from the basics and we'll move on into a little bit more advanced stuff, as well as kind of tie it all together with SimpliPhi products and how we have solutions for these various applications. Okay, so basic definitions here: coupling. And really just, again, we're talking in the context of a PV system in this case. And really the way I look at it is how solar panels are coupled to a battery relative to charging. So that is really what we're talking about when we're talking about coupling. So the two types we're talking about are AC and DC coupling. AC coupling, so what we're talking about is coupling AC power from inverted PV array to be converted into DC power for battery charging. AC coupling is mostly associated a lot with retrofits. A lot of the time, a customer adding a battery after they already have a grid-tied PV system. DC coupling, this is coupling DC power from a PV array with charging regulations in order to charge a battery bank before being inverted to AC power. So again, we've got a charge controller, and we'll get into all of this in a lot more detail, but DC coupling really keeps the power as DC from the panel, regulates it, but gets it to the battery before being inverted. So we'll start with a little bit deeper dive into DC coupling. So DC coupling, DC power from generation to batteries. So in this case, we're really talking mostly about PV, though DC coupling could relate to wind, could relate to hydro, still DC coupled typically. So we're using charge controllers in this case. That's kind of the main component that differs. We want to use a charge controller, and we're controlling the DC power voltage in amps for charging the battery. So, you've got a certain PV voltage coming out, and we want to see, what we actually want to put into the battery. We'll talk about that, I believe, on the next slide a little bit more. And we're still supplying AC from inverter to power loads. So the inverter itself is what's still inverting after the battery's been charged and powering those loads. PV arrangement considerations, and we will talk, I think, more about this, and I think I could cover it maybe a few too many times in this, but a big difference between AC coupling and DC coupling tends to be the PV arrangement. So how many can you put in a string? So DC coupling systems typically would have less that can be put in series as far as panels. So it makes it for a little bit tricky of an install. But that being said, that's changed a lot even as of late, where we're seeing more DC coupled systems that are able to support higher voltage strings, and getting close to being kind of on level with micro inverters and string inverters as far as PV size, string size. Okay, so what does a charge controller do exactly? And for anyone that's maybe in the charge controller industry, I'm sure I'll botch. This is a rough cut, and I'm sure there's way more to add. But in terms of for this presentation, all really what we're looking at is charge controllers regulating DC voltage and current going to a battery bank to hit specific set points and battery limitations for charging from a DC source. So again, like think about PV array has, let's say 80 volts at 9 amps coming out of a string in maybe a 3-panel setup. And we need to drop that to the charging voltage. So let's say it's a 48 volt SimpliPhi battery. We want to use 56 volts. So the charge controller actually drops it down to 56. Obviously, the current's going to go up. So we have more current going into the battery at that specific targeted voltage. So that's really what the charge controller's function is in this case. Again, it can be both PV and wind and hydro. There's different DC sources. It doesn't necessarily just need to be PV. And then something to consider is MPPT versus PWM. So maximum power point tracking versus pulse width modulation. Really, if we're going to look at the grant, just definition wise, MPPT detects solar panel output voltage in real time. So the system can charge battery with the max power. The PWM modulates width of pulse under certain conditions. So battery charges under these conditions. So it's a bit more off and on as I look at it. I tend to lean towards the MPPT when it comes to lithium batteries, but they really do both still have their cause. I will say most of the time you're going to see most charge controllers these days coming out as MPPT, maximum power point tracking. So this is a little bit confusing. So first I just want to point to something. You will notice right here, these are actually not DC optimizers or microinverters. This is just rapid shutdown compliant components tied together with this this Wi-Fi connection, this shutdown. So it's kind of confusing. Probably should take these out when looking at DC coupled, but really what we want to look at for DC coupled in this case is the panels going into this. So the SolarX here actually has a built-in charge controller. So it's actually charging this battery bank before either going out to critical loads or going out to the main loads and the grid. So again, PV is being charged before it is being inverted. That's a DC coupled setup. DC bus bars, important in the DC coupled setup. So what really lands on that DC bus bar? Batteries, charge controller output. So that's coming out, the PV goes into the charge controller and out, and the inverter's battery connections. So it's really important to think about. I think I've seen a lot of mistakes being made in the field of people basically kind of thinking the flow of energy is more linear, as it's, from the PV to the charge controller, to the batteries, to the inverter, and in a big line. We really want that common connection so that the power can flow where it needs to flow. So if if the batteries are full, we know where it's going. You don't want everything pushing through the battery. We love this common connection DC bus bar. So, that could be a variety of options, really, when you're looking at setting up a system from a combiner box to the DC bus bar and certain power panels that come with the inverters to something really basic like this. Okay, so now we're going to go through a little bit more of a in-depth look at AC coupled and its definition. So what we're talking about AC coupling, again, we're just going to really talk about PV a little bit more in depth. I think that makes it a little easier to understand. Talking about PV, AC power coming off the roof. So this is probably micro or string inverters. And it obviously doesn't need to be the roof, it can be ground mount, it's just kind of a phrase. But it's really that means that you are inverting the This is just making sure I don't have any questions here. Okay, perfect. I see a few questions coming in. No worries. We'll definitely get to those at the end. So just when you have the PV array and it's being inverted already, so then now we need to decide how do we get that energy, that power being produced back to DC, because that's what the battery needs to charge. So basically what we're doing is we're taking that AC and we're going through the internal charger of the battery based inverter. So not through a charge controller, but through the actual charger of the battery, of the inverter itself. These chargers, so you hear the word inverter charger on a battery system. These chargers are for AC power, being converted to DC. So that's the kind of big difference. Whereas the charge controller is just taking DC to DC. PV arrangement considerations. This is a big one, I think. First consideration is, if is the system already in place, grid tied system, then most people are going to go AC coupled. You can have bigger strings as well, even if you are building it from scratch. So as far as what's being inverted, while we are charging through the inverter charger, we are still inverting that DC out of the inverter itself to power loads, sell the grid, whatever needs to happen. Sorry, I was stuck on that slide there. So again, we're using the inverter's built-in charger, not the charge controller itself. It is similar to charge controllers as far as its charging profile, things like that, but it's taking an AC and converting it to DC, not just taking DC and regulating it. We can look at using a generator, looking at if you're charging a battery from a generator or the grid or a grid type PV array. Those are all kind of forms of AC power going through that charger. AC coupling specifically, and really in this term, we're talking about PV specifically. Okay, so frequency shifting is kind of a term that I actually took it out of the main definitions. I put it in here, specific to AC coupling. In this case, frequency shifting, really in this manner, we're talking about shifting is a mechanism used in battery-based inverters to regulate or control a grid-tied PV inverter's output. Not just that, but really, that ability to keep that grid-tied array running when the grid's down and charge that battery. So it's controlling AC frequency to regulate the charge itself. And the grid, when we're looking at grid-tied inverters, and we need to consider that, if a system's already in place, let's say it's pretty old, maybe it's got some M250s on it, we need to consider that maybe the battery-based inverter is so new that its frequency watts profile, the way it actually uses its ramp and regulation might be a little different than how it might interact with a brand new microinverter. So it is always important to kind of confirm with, I would typically say confirm with the grid tied inverter. So if you're, if you're hooking up to an N phase, let's say you have a customer that has an N phase system already in place, but some older N phase, and you're putting a brand new battery and battery based inverter system in, it's going to have to frequency shift to charge that battery. When that grid's down, I would recommend starting with the grid tied inverter company. Call Enphase and say, hey, what do you know about the AC coupling between this inverter and your M250s? They're pretty savvy when it comes to that stuff. They'll typically know. Okay, so kind of just to show you the progression here, again, retrofit being, I think, really the biggest use for AC coupling. We've got our PV panels going to these microinverters. Maybe this is a combiner, maybe it's a critical loads panel, or at least a loads panel put in for a combiner's purpose, and out to the main and the grid. Basically, all we're doing is shoving maybe not the best word, we are installing a battery-based inverter in between the main, and this will be our critical, and our PV system. Now we have the batteries here, so power still flows through and out to the grid selling, but we have the ability to charge the batteries from the grid, from the PV source, as well as when the grid goes down, we disconnect here. Now we can frequency shift, control these PV panels, as well as discharge both the battery and use the solar to cover critical loads. Grid comes back on, it reconnects itself. Okay, let's talk a little bit about applications. DC coupled applications. I think the biggest one people associate is off-grid. Off-grid is still the biggest, I would say, use of DC coupled systems. Something important to kind of note is, so if you look through our materials before, you might notice that we call out two-stage no float for a charging profile. That relates to AC sources. But DC source, like a PV array, you can use float all you want. Why not? You know, we can use that float. We don't have to worry about, you know, wasting power because it's coming off of the solar array. So we can definitely let that power through and use that float charge. So that being said, off-grid being the biggest, battery backup still absolutely doable. I think there's a misconception that maybe DC coupled only for off-grid. If you're building a brand new system and it's grid tied, I suggest going DC coupled. So if your customer's asking for they want a PV array and a battery right out of the gate, there's actually some huge advantages to going DC coupled right away. And things like, basically you can use TOU function. So AC coupled can use TOU a little bit, but it's not true time of use. You can use TOU. You can do peak load shaving when it's DC coupled grid tied. The charging from the PV is a little smoother, as it really doesn't see a blip. It doesn't change from, you know, one operation to frequency shifting. It's just doesn't even really notice. The charge controller is not going to notice the grid's down. And, you know, again, I actually go this way. You can still do things like cell and those kind of features. So if your customer is asking for batteries and storage and PV right out of the gate, makes a lot of sense. There's also financial aspects of it where you can actually apply for the ITC with everything all at once, versus when you put a battery in afterwards, you can't really collect on that portion with the battery itself. Large scale C&I, definitely doable when it comes to DC coupled systems, you know, big DC to DC converters and optimizers. I won't spend too much time when it comes to commercial stuff. And I definitely don't claim to be an expert there one bit. So AC coupling applications, biggest thing that comes to mind, battery backup. You know, you already have an existing PV system. Great time to put a battery in, use an AC coupled arrangement. Something to note is don't use AC coupled off grid. It really does not work well. The only thing I can think of that works kind of set up for off grid is the Sunny Island, Sunny Boy setup. That's SMA. That is kind of specifically designed to be able to work off grid while AC coupled. But typical AC coupled systems, I would not recommend. I apologize. I did not plug in my computer. Everyone just give me 2 seconds here. Let me plug it in. All right, everybody. Sorry about that. I'm sure you heard the dog barking in the background too. Okay, let's jump right back into this. Hey. Sorry, everybody. Give me 1 second here. Okay. Computer's back plugged in. Hopefully dogs will stop barking soon. Okay, back to it. So back to AC coupling. Large scale C&I, I do see also a lot when it comes to AC coupling. We do see a lot of that because of PV arrangements. You can do large strings, large arrangements. Adding a battery to an existing large scale system makes a lot of sense. All right, I apologize, everybody. I will be right get back again. I'm gonna put the dog outside here. All right, off to a rocky start there, but back to it. Okay. So there are some limitations when AC coupling that we want to consider. Time of use, I already mentioned this one a little bit, but time of use can be kind of tricky when it comes to AC coupling. The solar inverter, for instance, does have the claim to be able to use time of use, true time of use, while AC coupled. Most battery-based inverters do not have this ability. They can use what's called grid timers, which is not a true time of use function, and it's a little trickier. Self-consumption is technically not possible in most of these cases as well, meaning that you can't just use your battery in the middle of the day. You kind of have to say, don't use grid versus use battery. Whereas DC coupled, you really are using that battery right out of the gate. Peak shaving, again, more of a function of a DC coupled system. All right. So looking at applications, retrofit versus new system, and the PV considerations. I feel like I've harped on this a lot, and I always do during this presentation, but it definitely comes down to, as an installer, one of the biggest factors I see people kind of look at. Existing PV, so the system's already in place. Maybe you were the installer, maybe you weren't, but there's already a PV system in place. I would almost never recommend going DC coupled if there's already a grid tied system in place. We really want to not have to rewire everything and rework everything. So we should definitely just go ahead and go AC coupled in that case. Again, there's a misconception of DC coupling that it is really, not designed for grid tied, but it absolutely is. And I kind of already talked about, there are huge advantages to going DC coupled grid tied. But again, I wouldn't do it if it's a retrofit. I would only do it if it's kind of a new system. As far as efficiency, that might be called out as well. Some people might say AC versus DC coupling, there's an efficiency difference, as AC coupling tends to be a modular level as far as optimization goes. Still possible when it comes to DC coupled as well. We can add those DC optimizers on. We can get that same level of optimization. Okay, we're going to talk a little bit about rapid shutdown, kind of NEC stuff here, and how it relates to AC versus DC coupling. Won't spend too much time on it, but we'll very briefly go through, as I think it's really a super important topic, and it's only going to continue to become more important. So DC coupled and RS compliance, so that rapid shutdown compliance, first and foremost, my biggest disclaimer is look at local jurisdictions very first, as each one's can be a little bit different. So you never know exactly what you're going to get. Don't, if one area is one way, you might get a completely different inspection in a different area. So it's just good to check and make sure you're aligned with your local inspectors. Something to think about when it's like DC coupled, shut-off box might be just fine. So maybe, if it's a ground-mounted system, your shut-off box into the home, that's probably okay just to call it that. That's your RS compliance. DC optimizers, though, you can definitely get them. Things like the Tigo, where it's rapid shutdown compliant and it's an optimizer, or it's just that rapid shutdown attachment. So like if you have, let's say you're building a brand new system on a home that's in a residential neighborhood, it's on the roof, probably, and it's DC coupled, probably the inspector is going to want modular level shutdown. So you would go with something like these, either DC optimizers with that RS part built into it, or just the straight rapid shutdown components that connect to each panel. Remote trip breakers. What I mean by this is this typically relates to the battery and being able to shut down the battery itself, which is becoming more of a rapid shutdown requirement. I don't see it everywhere because it's not specifically called out in the code. It's a little vague still, but it is definitely becoming more of a requirement. There's definitely options for that as well. If you're looking at something like the Solarc, like our Access built with that Solarc, it actually has a single button shutdown. So it's a single point shutdown that can control the PV and the battery and kind of fills both those needs. AC coupling is a little bit different when it comes to rapid shutdown compliance. You know, if you have microinverters, let's say, or a string inverter with optimizers and shutdown built into it, adding that battery in line typically doesn't change your rapid shutdown compliance. The only time that you would have to add anything special onto an AC coupled system that was already rapid shutdown compliant when adding a battery is if you require that battery remote trip where you can make sure that the battery disconnects as well as the PV. And in that case, we're really just looking at, again, a single button or a remote trip breaker. But really, if you were like set up with microinverters and they were all rapid shutdown compliant, you're probably pretty good. So some kind of diagrams here, DC coupled. So again, these would be just rapid shutdown components. Here's your initiation switch. So the Solarc in this instance has the ability to de-energize not just the PV from this switch, but also the batteries themselves. In the AC coupling, I like Matt's note here. I would agree with that. I know he put that one in. Not applicable for all jurisdictions. I can't express that enough. It really does change so much. So don't hop on your inspector and say, well, SimpliPhi said this, because it's their court they pick the rules. So it's just good to always check before. That being said, I have seen this setup work a lot when it comes to this. So like, again, you've already got a PV system in place and its main point of disconnect is just that disconnect box, clearly labeled. Adding this battery in, if they're not going to require battery shutdown, does not, you're good. You don't even really need to change anything in this system to continue on that inspection pass. Okay. So we are going to go through a little bit of system design considerations. Some of this I might skip through fast as we've talked a lot about it during the presentation, but I think I've kind of harped again on this idea that we're talking about, PV considerations, where it's, how do you string your panels, and that's really one of the biggest differences between DC and AC coupled. So wiring runs are going to be a little bit different. I'll skip kind of past the PV stuff because we've talked about it a lot. But what I want to look at is DC coupling, and grid down is a lot different in a DC coupled scenario. I think there's less of a blip. It doesn't change so much when it comes to charging. And you still can cover this critical loads panel, and it's the same design other than the PV side of things. Still can disconnect, reconnect from the grid. Now, AC coupling does kind of have that idea, where you're pushing power a certain way, and when the grid goes down, it does have to change its look at how it's going to charge the battery now. So it's ramping up the PV now, and it's kind of changing how it functions. So it's not as smooth, in my opinion, when it comes to that. Though, again, the PV considerations, larger strings, less wiring, and we can still power those critical loads and power the batteries from that PV array. Kind of related to CNI. Again, I try not to jump too much into CNI stuff, but large PV systems, DC to DC equipment is built out huge, and you're probably gonna need optimizers when it comes to these huge arrays. So that's always something to consider. I see a lot of big CNI projects go AC coupled because they have these larger string options. I think SMA makes a big one. That's like, you can run, 40 strings or whatever into the thing. So I do see that a little bit more frequently when it comes to large scale. That being said, though, DC, big MPPT charge controllers and DC equipment does exist a lot in the commercial and industrial space as well. Okay, let's talk a little bit about Phi products and kind of bring this all together. What does SimpliPhi have, and how does that relate to AC and DC coupling? First of all, our standard batteries, which now it's not just the Phi batteries, we also have our SimpliPhi batteries. But both those products, again, are designed as like these small little 3.8 kilowatt hour building blocks that you can expand on, scale up. They don't care about DC or AC coupling. It's really more related to the battery-based inverter that they're hooked up to. So, what they don't really care if it's, they get charged from DC either way. But if it's DC or AC coupling, the batteries don't necessarily care. There are some considerations as far as PV sizing goes. When it's AC coupled, you're a little bit more limited, which is all outlined in our manual, but really they don't care. Something to consider, if it's AC coupled though, you're going AC to DC back out to AC. Whereas when you're DC coupled, you're really just going DC to AC. So there is a little extra conversion there in the AC coupling. 48 volt out of these. So we do sell this battery in 24 volt. I would not recommend 24 volt for AC coupling. It's pretty rare that you'll find a battery-based inverter that's 24 volts that supports AC coupling. So I typically always would recommend 48 volts. We do have our Access. This is our all-in-one energy storage system that is NEMA 3R rated, so it's outdoor ready. Comes in both Schneider and Solarc. When it comes to DC and AC coupling with this unit, we do have a few different options. So with the Schneider unit, it actually comes AC coupled standard, and you need to purchase the different version, which is the DC coupled. And that DC coupled option has that charge controller in it. The Solarc, on the other hand, does not. It doesn't matter how you buy it because it actually has the charge controller built in internally. So it will work DC or AC coupled, really, no matter how you buy it, other than maybe a little bit of programming difference. Again, grid tied compatibility for AC coupling and specifically our Access unit. If it's our, this is our all-in-one, so definitely reach out to us if you're confused if maybe your grid tied inverters are going to work properly with one of our Access units. We can help you out. We can figure it out for you. And sizing considerations. I just mentioned this a little bit. So the PV to battery when you're AC coupled needs to be a certain size. So you need to make sure that so let's say you've got 14 kilowatt hours of battery. Your PV array can only be 7 kilowatts. And that's all outlined, by the way, in our manual. So if you're looking for those exact figures, section 3.1.1 kind of talks about that. But you are limited because sometimes the PV in an AC coupled scenario will kind of dump into the battery. We want to make sure the battery can handle that, doesn't get fried. We don't really want to rely on frequency shifting to ramp down that charge rate because sometimes it doesn't work perfectly. DC coupled, we don't have to worry about that consideration. You could have a pretty large array on the charge controller and it will do limiting. It'll limit the array into the battery with respects, of course, to the charge controller's own limits. Automatic transfer switch built into the Access, whether it's DC coupled or AC coupled. I think it's really great as far as outdoors systems and being, kind of geared towards being really geared towards, everything's outside, all the equipment's outside. So leaving this outside makes a lot of sense as well. So again, these numbers are kind of what I was talking about as far as AC coupling PV limitations. These might even be a little outdated. So I would just check out section 3.1.1 in both the Access manuals, and you'll get the most recent numbers when it comes to max PV size related to the Access unit that you are purchasing. Okay, design tools, looking at, what you might need to help out when it comes to DC and AC coupling and setting things up. You can always look at our manuals and spec sheets, integration guides, as I just mentioned. You can call our tech support, 805-640-6700, and it's option 1. You can email us, whatever works. We also have some pretty handy tools for this as well. This one's a little bit more basic. This is just a basic sizing tool based on kilowatt hour consumptions. But if you're going AC or DC couple and looking to kind of get a better understanding of system design, use this system battery sizing tool. It actually uses the idea of if you are DC or AC coupled and helps with some design considerations there. So just some helpful tools there. If you're actually interested in more about our tools, I actually have a whole webinar on tools that we offer. So I'd check that out. All right, a little bit about our Elite program, and then I'll go into questions here. So this is our Elite Installer Qualification program. First and foremost, it is not a requirement to install our batteries to actually go through this program, it's actually an added benefit for those that are already installing our batteries. So one of the requirements is that you have 2 installs done. If you do already, apply for this program. It takes like 10 minutes. The application is really easy. You'll end up as a little dot on our where to buy page. So as people go through the website, they will see you as somebody that's gone through this certification process, and that you're that dot that they're going to pick to install their battery. We don't necessarily give people your contact info directly. They get it through the website. So they'll just see you in their area and they'll pick you as the installer. So it definitely gives you a lot more visibility as an installer that uses our products. And you also will end up on our IQ newsletter and maybe even be featured on our podcast and different things like that. So there's a ton of benefits all outlined on the page. Just give it a look if you are interested in that program. It's really easy. Go to that page, scroll down, you'll see the application. It's all online, and it's really easy to fill out. This slide's a little bit out of place. I know that's kind of a wrap up, but looking at what, again, our messaging, what we're doing, why all this is so important, accelerating the energy transition, reimagining the power grid, building a more resilient energy future, which to me is really kind of the biggest one I'm seeing right now, is driving people towards, whether it's DC coupled or AC coupled, battery storage and really distributed assets, and continue to deliver economic value. All right. So first and foremost, before I jump into the questions, again, CEU credits, if you need them for NABCEP, email training@simpliphipower.com. You can see it right here. I'll leave that up while we answer questions. Email me, make sure your full name is in that email somewhere, how you want to look on the credits, and I will email you back a certificate. All right, let's open the questions up. So what are the most common ways to provide OCPD for DC distribution to individual batteries from DC bus? I'm sorry, I don't know that acronym. What is OCPD? If you don't mind writing in, I can answer that one as I go through. So on to the next one. A longer term question: is SimpliPhi considering diving deeper into the microgrid arena, perhaps partnering with control systems such as, and name a few there. Yeah, actually, we do have some microgrid applications. We have our high voltage product, and we do actually work with, I think, a few of the control systems, though we're pretty agnostic when it comes to that. So you can actually kind of work with that, with whatever you want. But we do have tons of different setups using that. Okay, I see. Thanks, Bailey, for answering my question. Overcurrent protection device. So what are the most common ways to provide an overcurrent protection device for DC distribution to individual batteries from the DC bus? Well, good question. Really, if you size everything properly, this shouldn't even be a problem. The overcurrent protection is really not even needed. We do have some overcurrent protection on our batteries, but it's a bit larger. If you want to put in inline breakers between your combiner or on your combiner and each individual batteries, I've definitely seen that as well. And that's totally fine. And some actually battery combiners have spots to put those breakers in. How does the utility know how much power you rolled your meter back by when the power first goes through a critical loads panel on AC coupled system? How much power you rolled your meter back. So I think you're saying how much power you sold to the grid. Utility, sorry, I'm just going to read your question one more time, Parker, here. How does the utility know how much power you... Well, the utility simply just reads off of the meter itself. So, if you add in a battery system, the only difference maybe is that the battery is charging a little bit from maybe solar or the grid. But as far as, all the power is still flowing out to the grid in normal operation. If the grid's up, even, through the critical loads panel, the PV coming through there, it's still flowing out to the meter. So it's still clocking out everything that you've create as excess, and still you're getting paid for what you're selling. And that meter will read that. What inverter would you recommend for a new 115 kilowatt solar system, 3-phase commercial? I have seen a lot of people use the Dynapower stuff, built-in MPPT charge controller as well, and build out those bigger systems. Not too huge, 115 kilowatts, 115 kilowatts, kind of that sweet spot for like microgrid stuff. So I'd say look into Dynapower. Are all systems compliant to UL 9540 and related IEC standards? So I think, so you're talking about 9540A, so the actual testing protocol, which we have gone through with our products. As far as 95, and I might screw this up here. So yes, I believe so. And then with 9540, which is the all-in-one system UL standard, not A, the actual testing protocol, but 9540, we do have our access units are approved for 9540. Specifically, though, the Solarc one access unit is the one we got approved. With the Schneider one, you have to pull out the components have to be separate as far as how you list it. Okay. Cool. I see some comments about Midnight making some DC breakers and some DC panel boards. Absolutely. And their combiner boxes are kind of my go-to as well. So, I see you mentioned very useful for DC loads, such as in DC microgrids. Awesome. How do I test a battery to determine whether it is good or has failed? Unlike lead acid batteries, the rapid falling voltage or specific gravity measures can't be done. Well, voltage will drop very drastically lithium batteries do have the tendency to drop a little bit more than normal, than like a lead acid battery, just a normal operation. But if they're like tanking, like going, 52 volts and then just dropping down to like 5 volts or something, probably have a bad battery. But really, lithium batteries, they can take a lot of pressure, but it's mostly pretty obvious when they are failed, as they will not hold the load or hold a charge properly. So I have an N-phase system using M250s in microinverters. Have you seen anyone have success with the frequency shift issue or that model of the microinverter? Yeah. Okay. Well, no, and actually, I see you're saying, maybe not asking N-phase because they have their own storage. They're really helpful. Actually, they've always been helpful, in my opinion, regarding any setup that is hooked up with their systems. I have seen people use the M250s. I typically suggest the Schneider Pro, XW Pro, as the inverter to go with when using those older microinverters, as its frequency shifting is pretty dynamic. It seems to work best. The expectation really should be that if you're using like an older microinverter like that, frequency shifting might not be as flawless as it might be with like an IQ8 or something. So it might be a little bit more off and on versus kind of that ramp factor. How do you incorporate a battery combiner box with 24 amplified batteries? Do equal lengths of cable from each battery go to a battery box? I would say if you've got some specific design questions, either ask, I would definitely say we want to look at that in a little bit more detail. So maybe ask, one of our salespeople who are engineers typically as well, or a tech support, and we can help direct you as well. But really, if you're using 24 batteries, you can either, same length, same size cable up to a common connection point, or I see a lot of people use, if you've got the room for it, you can use battery terminal bus bars that can go across multiple batteries, and then you cut down on how many cables you're actually running. Awesome. Are your high voltage solutions usable for ESS systems such as Enphase or SolarEdge rather than LG Chem? No, not really. The high voltage is really designed for large scale stuff. So, the smallest building block you'll get is still kind of too big for that, for connecting with the SolarEdge or the storage. I know that what you're talking about there, using that high voltage versus that 48 volts. Honestly, it seems like the industry is really shifting towards 48 volts. I know that LG still makes their higher voltage stuff, but either ESS or or low voltage seems to be the direction that things are moving towards. So no, I wouldn't use our high voltage in that situation. All right, looks like we're all out of questions here. I just wanted to say thanks everyone so much for joining. If you have any other questions that come up, feel free to shoot me an email at the same email address. Again, go ahead and email me if you need CEU credits for NABCEP, and I'll send you over the certificate. Thanks everyone, appreciate it.